Welcome back. Today, let's look at tangential annular flow. What do we mean by that? There are two concentric cylinders, okay, and we are looking at a liquid that is placed in the annulus or the annular space between these two cylinders, and one of those cylinders or both of those cylinders could rotate. When that happens, the liquid is forced to move in a tangential direction. Right, the velocity at any point is tangent to the radius, and that's why we call this tangential annular flow. This has very many interesting applications. We have used it in our own research some years ago. I'll probably give touch upon that also in this lecture. Tangential annular flow between two concentric cylinders is used in something called Couette flow rheometers. Such a flow is called Couette flow, or is one of the examples of Couette flow. So this flow is used in Couette flow rheometers to measure the viscosity of a variety of biological fluids or bioproducts such as xanthan gum. Okay, the Couette flow viscometer works on this principle. It is also used to study the effects of a defined shear on cells. The shear range is rather narrow when we use this kind of a device, and that's the reason why we used this kind of a device when we wanted to study the effect of defined shear stress on cells over the entire cultivation over a period of about 48 hours plus and so on. So let me tell you that in a little while from now. So let's consider the tangential annular flow of a Newtonian fluid. We'll deal with Newtonian fluid. You very well know that if it is not a Newtonian fluid, you'll have to use the other complex equation. You just cannot use the simplified one with constant mu and rho and mu for a Newtonian fluid. So that's the main difference in terms of approach. What we are interested in is this, as usual. We are interested in the tangential velocity profile between the cylinders because we get a lot of relevant information if we know the tangential velocity profile. And the relevant shear stress distribution, this is directly relevant if you're looking at the effect of shear stress on cells as we did in some of our studies. And we're also interested in here to find out the torque to turn the outer shaft. So our analysis is kind of focused towards these aspects. Okay. I'd also mentioned earlier that we look very many different things. We are working out problems as a part of learning itself. Okay. Then of course you'll have your assignment aspects to take care of to strengthen your understanding in the given context or within the limitations of the given context. So if you want more problems, please look at the end of the textbook. You have quite a few problems there which you can work out. However, the problems have been integrated into the class itself. In fact, tutorials, as they are called, are a part of class itself in this class design or in this course design. Okay. So look for it and don't feel that there are no separate problems. I've been projecting problems first and then giving you solutions in the context, giving you very general solutions in the context, as well as solving the problem in the process. Okay, so we are doing all that as a part of this course. Coming to this, I have posed the problem as this. We are interested in the velocity profile, the shear stress distribution, and the torque required to turn the outer shaft. And all these we want to do at steady state because it is the flow will be at steady state most of the time. Initial, probably a few minutes it will take to stabilize, and then when you shut it off, maybe it might take a few minutes for it to dissipate and so on and so forth. Then it may not be at steady state, otherwise it is going to be at steady state. The properties of interest, which are the velocity, the shear stress and so on and so forth, at a particular point in the flow do not change with time. Okay. And that is how pretty much the entire flow is going to be over the entire period of cultivation in our, as it was in our case. So this is the figure here, schematic here. This is the longitudinal section. You have the axis of the cylinders here. You have the inner cylinder represented by these two lines. You have the outer cylinder represented by these two lines. Okay, it's a cylinder. You cut it like this, it's going to look like this. And this is rotating in this direction with an angular velocity of omega naught. If you look at it from the end, one of the ends, it is going to look like a concentric set of circles. Our terminology is going to be like this. You'll have, let us take the outer radius as capital R and the inner radius as some kappa times R. So kappa gives you the fraction of the outer radius to the inner radius. So this is rotating at an angular velocity of omega naught. The linear velocity is v theta. The tangential velocity is v theta. We are going to take, in this case, that the outer cylinder alone rotates. Okay, there are some advantages to that geometry or that scenario where the outer cylinder rotates. Theoretically, any of the cylinders can rotate or both of the cylinders can rotate. Okay. However, there are some wide ranges of Reynolds numbers over which you can assume the conditions that are relevant for us if the outer cylinder rotates. The inner cylinder is stationary here. So this is what we call as the Couette flow device. As you can see, this is a cylindrical system, and therefore the most convenient set of equations to use from the tables, hopefully you made a copy, is the equation A2 from table 3.4-2. Okay, and this is for the R component. Let us start with the R component. Let us apply that momentum balance to the system and let us see what we are going to get. This is the R component. Just check the equation, go back and see, write it down. Rho dou Vr dou t plus Vr dou Vr dou r plus V theta by r dou Vr dou theta minus V theta squared by r plus Vz dou Vr dou z equals minus dou p dou r plus mu of dou r 1 by r dou r r Vr of r Vr plus 1 by r squared dou squared Vr dou theta squared minus 2 by r squared dou V theta dou theta plus dou squared Vr dou z squared plus rho gr. So this is the momentum balance equation for the R component in the cylindrical coordinate system. Let us see what are the terms that are relevant for us. We are doing a steady state analysis, therefore any time derivative is set to 0, so this goes out. There is only a V theta here, right? You can imagine this. There is no Vr, there is no Vz. So Vr is 0, so this term goes to 0. V theta exists, but Vr is 0, so this term goes to 0. V theta, of course, is very much there. Vz is 0, and therefore this term goes to 0. Dou p dou r, let's keep this, we don't know much about this. There is no Vr, therefore this goes to 0, this goes to 0 for the same reason. And here, V theta is the same at any theta, constant angular velocity, right? Therefore, V theta is not different at different thetas. In other words, V theta is not a function of theta. Therefore, the derivative with respect to theta of V theta goes to 0. And Vr is 0, so this goes to 0. And G is acting in this direction, therefore Gr, which is perpendicular to that, there is no component of G in the R direction, therefore this goes to 0. So what remains is minus rho V theta squared by R, which is this term, equals minus dou p dou r. Okay, so this is what we get from applying the momentum balance in the R direction. Let us call this equation 3.4.3-1. Now, from equation B2 of the same table for the theta component, the first one was for the R component, this one is for the theta component. You get this equation. And if you see which terms are relevant, there is no this is at steady state, there is no variation with time, so this goes to 0. Vr is 0, so this entire term goes to 0. V theta is there, but V theta is not a function of theta, therefore this derivative goes to 0. Vr is 0, therefore this vanishes. Vz is 0, therefore this vanishes. Of course, you have equal to minus 1 by r dou p dou theta, that remains. Here V theta is there, therefore this remains. Okay, there is no Vr, right? Yeah, this remains. Here, yeah, V theta is there. Yeah, then there is no Vr here. Yeah, so this remains. Here you don't have V theta as a function of theta, so this goes to 0. Here you don't have a Vr at all, leave alone it being a function of theta. Vr itself is 0, therefore this goes to 0. Here V theta is not a function of theta, so this goes to 0. And there is no g, the acceleration due to gravity component in the theta direction. Therefore, g theta goes to 0. So what we have remaining, please ignore this. I think this is a leftover from some previous thing. This certainly is there. And P is not a function of theta because the points at different angles at the same radial position cannot have different pressures. Okay, so P is not a function of theta. So that gets out. Therefore, I think, this goes out. So what we get from this is the left hand side is 0, the right hand side only this remains, which is mu, and since r is the only variable here, I can replace the partial with the total derivative, d dr 1 by r d dr of r v theta, that equals 0. This is equation 3.4.3-2. Okay. Now the third component, which is the other equation from the same table, the cylindrical coordinates table. You will have this, please write it down and check. Let us cancel the irrelevant terms. The process is at steady state, therefore no time derivative. This goes to 0. Vr is 0, this vanishes. V theta is there, but Vz is 0, so that goes to 0. Don't even worry about function of theta. Vz itself is 0. And here this Vz is 0, so that goes. Minus dou p dou z plus mu times 1 by r dou r, r dou Vz dou r. Here Vz is 0, so you don't have to worry about this. Vz is 0, Vz is 0. This entire term drops out. And of course, you have rho gz, because gz is the acceleration due to gravity, that equals g. Okay. So what is remaining here is 0 equals minus dou p dou z plus rho gz, which gives us the familiar relationship that we have already seen earlier. Anyway, let's keep it as it is. 3.4.3-3. Now the boundary conditions for integrating 3.4.3-2, which is this equation. Okay, this is the differential equation. Is at r equals kr, the inner radius, or kappa, or let's call it k. R equals kr, the inner cylinder radius, v theta equals 0, because the inner cylinder is stationary. And therefore, the liquid that we are considering, the layer that is closest to the inner cylinder will stick to the inner cylinder and not move. And therefore, v theta is 0. And at r equals r, the velocity v theta equals the angular velocity times the radius. That's the definition of linear velocity, angular velocity times the radius. And that is the situation at r equals r. So we have two boundary conditions. We can solve that second order differential equation. So you have this equals 0, and therefore we can take this as this being a constant, then this goes to 0. This equals to 0 is irrelevant here, therefore d dr of this of this being a constant is the relevant thing. 1 by r d dr of r v theta equals c1, and therefore d dr of r v theta equals c1r. And now just for ease, you could directly do it, but just for ease, If you set the product of r v theta as m, okay, you can take this as a whole function as, and or you could just look at this as m, that's easier. Then you get dm dr equals c1r, and therefore it's easier to integrate m equals c1r by 2 r squared, sorry, c1r squared by 2 plus c2, the c1r. Therefore integral of this is r squared by 2, c1r squared by 2 plus c2, and m is nothing but r v theta. Bring this back here. C1, it's a product, you need to look at it as that. This helps in the visualization of what the actual meaning is, and therefore it's nice to do this. R v theta is C1 r squared by 2 plus C2, and therefore v theta is nothing but C1 r by 2, you divide by r throughout, plus C2 by r. And now if you use the first boundary condition, okay, this we need to find C1 and C2 using the boundary conditions. If you use the first boundary conditions, we get r equals kr, okay, v theta is 0. So we get 0 equals C1 by 2 kr plus C2 by kr. And therefore, C1 is nothing but minus 2 C2 by k squared r squared. So we have a value for C1, we can substitute this here, use the second boundary condition to get C2. And that is what we have done here. Omega naught r equals, this is the velocity at r, equals minus 2 c2 k squared r squared times r by 2 plus c2 by r. Just substituted whatever we had for c1, and then we get an equation. You simplify this, 2 cancel, and r cancels with 1r, and you have a minus here. Therefore this is the term that corresponds to this, minus 1 by r k squared, and here you have 1 by r remaining, and if you further take r out as common, you get c2 by r, 1 minus 1 by k squared equals omega naught r, and this you could write as c2 by r k squared by k squared minus 1 by taking k squared minus 1 by k squared. It should be to the power of minus 1. Hold on. This is just the inverse of that. Okay, so let me see, equation tools. And put a minus 1 there. We'll copy this and we'll put it here, and we'll get rid of this. Okay, that's what this is, and therefore let's get back to this. Yeah, therefore we have C2 equals omega naught, r is already here, therefore r squared. Now this is 1 by, and therefore it goes to the other side, it's the same way, k squared by k squared minus 1. And C1 is nothing but from the same manipulations, right? We have C1 given here. C1 is in terms of C2, therefore need to substitute for C2 to get C1. That's what we are doing here. So C1 is minus 2 by k squared r squared, and C2 was omega naught r squared k squared by k squared minus 1. Therefore this will turn out to be r squared k squared will get cancelled out, 2 omega naught by k squared minus 1. Okay. So the solution is for v theta, expression for v theta, which is what we are after, is minus 2 omega naught by k squared minus 1 times r by 2 plus omega naught k squared r squared by k squared minus 1 times r. And if you take out common omega naught r squared by 1 minus k squared, you have r by r squared remaining here. You've taken out r squared, so you need to divide by r squared. There's no r squared here. And what remains here is k squared minus r, which can be written as omega naught kr squared by 1 minus k squared, r by kr squared minus k by r, which can be written as this omega naught r squared by 1 by k minus k. That's what this is if you take the k out here, and r by kr, 1 by r of course pulled out here, therefore r by kr minus kr by r, and which can be written as omega naught, so r squared and r, 1 r gets cancelled, omega naught r squared by kr by r minus r by kr divided by k minus 1 by k. Okay. So this is the usual form in which the v theta is written. Equation 3.4.3-4, we know the radius of the outer cylinder, we know the ratio of the two radii as k, and this is the v theta as a function of the radius in the annular space where the fluid is rotating. Okay. So we have an expression for the angular velocity. I think we can continue. We said we are after velocity distribution, shear stress distribution, and the torque. One done. So 2 more to go, but they are quite straightforward. The relevant shear stress distribution can be obtained using the expression for shear stress components itself directly in cylindrical coordinates given in table 3.4-5. So from equation A, you look at that table, go and look at that table. Tau r theta is what we are looking at. Tau, this is the, you could see the direction of action, the direction of motion. Because of the velocity in the theta direction, what is the velocity gradient in the r direction, which causes the shear stress in the r direction. That's what we're looking at. So tau r theta is minus mu r dou dou r v theta by r plus 1 by r dou v r dou theta. Okay. So this is what it is in cylindrical coordinates from that table for laminar, for Newtonian fluid. And since Vr is 0, don't even worry about not being a function of theta. There is no Vr, there is no velocity in the radial direction. Therefore, this goes to 0. This is the only term that remains, r dou dou r v theta by r. And therefore, we can replace, and since r is the only variable here, we can replace the partials with the total derivative. And we get tau r theta equals minus mu r ddr of v theta. V theta, we already have the expression from the previous derivation, so that we can substitute here. Omega naught r times kr by r minus r by kr divided by r times k minus 1 by k, which can be written in this form. Okay, just simplifying. Further simplifying, r dr, I'm just grouping the terms separately, differently, so that it comes to a certain form that can be handled. So just taking r inside here, we get this, which can now you can process this as r. I mean, this is 1 by kr, this is a constant, not a function of r, so this will drop out. This is the only term you need to differentiate. If you differentiate this 1 by r squared, you get minus r cubed, and there's a factor there that gets cancelled out. And therefore, you have minus 2 kr by r cubed. And here is another r that is sitting there. Therefore, I'm showing you step by step. Some of you might feel bored, so just fast forward now. Minus 2 mu omega naught r squared k, I'm just putting all together, k minus 1 by k times 1 by r squared, and which can be written as minus 2 mu omega naught r squared, k squared time divided by k squared minus 1. So all these are constants for a given situation, for a given omega naught, and the variation is proportional to the inverse of the square of the radius. This is equation 3.4.3-5. Okay. Why don't you plot this in C and just go to Excel, put in some number for this and just see what the variation of 1 by r squared is. You'll get a good idea. The form of the function is nice to see. Now, okay, so we have an expression for the angular velocity, the tangential velocity, as well as the relevant shear stress. And now let us look at the torque that is needed to turn the outer cylinder. We all know from basic physics that torque is nothing but force times the lever arm distance. Okay. So torque is the force. The force here is used to overcome the shear stress, therefore the shear force. So the shear force is nothing but the shear stress times the area. So shear stress times the area, the shear stress of relevance is tau r theta, okay, as we have picturized earlier. Tau r theta at r equals r, that would be the maximum, times the lever arm distance, and the negative sign before tau r theta is to overcome the shear stress by the fluid on the wall, and therefore minus tau r theta at r equals r, area is 2 pi r times L, the surface area of the cylinder, that is the relevant surface that we are talking about. Lever arm distance is nothing but the radius of the outer cylinder. You substitute the expression for tau r theta with a negative, you get this times 2 pi r L times r. If you simplify this, cancel out r squared is going to go, and there's a pi here, 2 here. You put all together, you get 4 pi mu omega naught Lr squared times k squared by 1 minus k squared. So this is equation 3.4.3-6. So we have an expression for the torque here. This can be directly used to design the Couette flow device and thereby decide on the motor characteristics that you need, the type of motor that you need, and so on and so forth, to provide this required torque plus more. We usually design with a safety factor, and that would give you the appropriate choice of the motor for this application. What I'm going to also show you is where we used this particular device. Okay, of course, this is used in a viscometer, as Bostwick the viscometer that we mentioned earlier, the Couette flow viscometer to measure viscosities. Okay, there's a certain way by which you can get the viscosity in terms of the other measured variables. That's what is used for as the basis for that viscometer design. Here I'm going to show you something else. Okay, here I think I need to show you that paper. If you go to my web page, look for a paper that was published in 2003, I think. This was the first author would be Susmita Sahu, and look at I think it's called macro level and genetic level effects of shear stress on cells. We would have used this kind of a device and appropriately modified it. We did it for the first time to be able to grow cells over an extended period. The use of Couette flow device for studying the effect of defined shear was known for a long time. Only thing is that people could not use it for more than a few minutes because the oxygen would become limiting. We found a way of providing oxygen continuously through air, but not affecting the flow profiles, so that the shear rate profiles shear stress profiles would remain unaffected. And the advantage of using Couette flow for exposing the cells to defined shear stress would be available. Okay, that is a contribution which was published in Biotechnology Progress way back in 2003. Please take a look at that for the application of one of the applications of a Couette flow device, this kind of a flow situation. We had to go through all this. Some of the expressions were available, some of the expressions we had to derive in order to design one such device. The device design was complex from a mechanical engineering point of view. You know, the space between those two steel cylinders is 2 mm. Okay, that is the annular space that we are looking at. And the outer cylinder rotates at 1500 rpm. Okay, huge rpm. And therefore it should not shake. It is of this about foot plus height, about 35 centimeters of height. Okay, so it cannot there cannot be any motion in any other direction except for this motion. To achieve that, Vaspan Industries, the person I worked with at the industry that I worked with at Mumbai when I was at IIT Bombay, he had actually gone to auto bearings, okay, to provide the needed mechanical properties so that it would rotate without any vibration. Okay. So that's the kind of situations that require high precision and so on and so forth. That provides it, we have done it ourselves, and we have used essentially the same principles to design that, the same equations we used to design. Okay, okay, I think we will stop here. I would have shown you that paper. I don't think I have that paper here on this computer, but there is a reference that I've given. You can go and see that paper. See you then. Let's take things forward in the next class.